Hello everyone, welcome back to Simoscope. In today's series, I have uh, a project where I'm going to design and simulate and analyze the flyback converter. Okay, I have used the MATLAB Simulink to do this, and all the calculations are done in ChatGPT, and we have a wonderful result here. Okay, what is the project about? Design, modeling, and analysis of flyback converter using the MATLAB Simulink. The project has a very specific parameters given. Firstly, moving into that, what I will introduce you what is a flyback converter. It is a DC-DC converter. However, this is an isolated DC-DC converter, and uh, where it is used usually when the low power switching mode power supplies applications are applicable. That makes no sense, right? So it is more suitable when very high DC input voltage is there and you have to convert it into the uh, low DC output. And another thing is you require the galvanic isolation between your source and your power source and your load. So what is galvanic isolation? It is like electrical, maintaining the electrical isolation. So by using, how do you do this? By using the transformer, and if we use the buck converter, you can still reduce the input voltage to the output voltage. However, you do not get the isolation. So using this isolation transformer, you are electrically isolating the primary source side uh, and the load side, and they are not electrically connected. That's why it's called as a galvanic isolation. So uh, this project in this project the topic the question has specified that our input voltage should be Vin should be 170 volt. Output voltage we required is 5 volt. So it is reduced to 170 volt is reduced to 5 volt. Then the output power should be at least 25 watt, minimum of 25 watt. Then the switching frequency of the circuit should be 100 kilohertz, and it also says the duty cycle should be 0.5. And finally, uh, the output ripple, voltage ripple or output waveform ripple should be less than 2%. And you have also a capacitor loss tangent or given as 0.1. Okay, now you can choose the load, and for simplicity we are going to use the purely resistive load. To move forward, I will explain you first the architecture of the flyback converter. Firstly, we have a DC source. Then second component is a transformer. In the primary side of a transformer is connected to the source, and the primary side of the transformer is switched using the MOSFET or IGBT, and this is a switch. And this switch is again controlled using the PWM generator, which is DC-DC PWM generator, and my duty cycle for the PWM generator is 0.5. Then at the secondary side of the transformer, I have one diode connected something like this, and a capacitor is connected in parallel to the load. My load is purely resistive load. Here I have current and voltage measurement blocks where I can get the output voltage and output current, and multiplying them will give me a output power. The scope is used to see the waveforms in a later part. So now moving on to the calculation and modeling part of the circuit, we are not just going to make things assume and make it ideal. Instead, we will calculate very detailed manner and consider all the parameters, all the losses. So first thing first is calculation of the load. Now you are given the power and the output power and output voltage, 25 volt and 5 amps. So 5 volt, 25 watt. So you are getting output current of I naught is equals to 5 amps. Now you have a output current. You can calculate the R load, the load resistance, by this formula V naught divided by I naught, and you are getting your load resistance as 1 ohm. Now for simplicity and understanding, we are going to use a load of 1 ohm. You can change the load and still get the current. So your output current will change when you change your load. If your load increases, like you have a load of R load is 10, then your current will become 0.5, right? So current is dependent on the load. Next is selection of your transformer. To select your transformer, very important thing you require is the turn ratio of your transformer. How do you get your transformer? So your output voltage of the transformer V out is given by this formula, ns divided by n primary, the primary turn ratio, number of windings in the secondary divided by number of winding in the primary, times V input, times duty cycle divided by 1 minus duty cycle. So using this formula, I'm going to find NP and NS, which is primary turns and secondary turn. This is a winding. And I have a duty cycle of 0.5, which is given. So by calculating this part, I'm getting 1. And finally, I have my primary NP divided by NS, which is equals to 34. So ideal turn ratio is NP divided by NP is to NS is 34 is to 1. But this is in case of the ideal cases or ideal transformer without any transformer losses. However, we cannot get by using this turn ratio, we cannot get exactly 5 volt at the output because of the transformer winding, transformer resistive losses, winding losses, diode and switching or MOSFETs switching losses. So to consider that, we have to tune this transformer ratio such that we get the simulated output of a 5-volt. So I have already done the tuning of the uh, transformer ratio, turn ratio, and at 34:1, I could get the output voltage of 3.057 volt. At 20:1, I could get 4.5 volt, which is good enough. Still, then I want to be at the higher side. So at 10:1, I could get 5.142. So therefore, I want to select my transformer ratio as 10:1. And from the calculated of 34:1, I'm selecting 10:1. By doing that, I'm saying that practically my winding for the primary winding should be 50 and secondary winding should be 5. Right? So you might be thinking, why should we put a drastic reduction in the turn ratio? Here 3.0475, we can't get a 5 volt, and current is also low. I mean, at this turn ratio, I will get my output current as 3, so my power won't be even 3 times 3, so it will be just 3 times 3, so my power won't be even I cannot get the minimum of 25 watt power, and therefore my converter will not be able to supply a required load power. Therefore, I have to choose 10:1. Now, moving forward, I have to find the magnetizing inductance. The formula is this one. So I have a primary inductance of the transformer as 1.23 millihenry. Now, secondary side inductance theoretically is 12.34. However, still very high. Therefore, I choose as 1.06, and it also this tuning is required because it affects the output voltage. Then the primary current calculation is required to calculate the uh, winding resistance. So transformer primary peak current is calculated using this number, and I'm getting a primary peak current is 0.69 amps, and my RMS, that means the primary side current flowing through the primary winding, is 0.28. Similarly, secondary side peak secondary current is 6.9 amps, and RMS value is 2.82 amps. Therefore, using these current values, I calculate the winding resistance. Now, to calculate the winding resistance, I have to also consider the copper resistivity, which is this value. Then I assumed my winding length to be 0.055 meter. Yep. Then finally I could calculate using the winding resistance using this formula, and the primary winding resistance is 0.367. Oh, sorry. After including the temperature correction, I could get 0.459 ohms. Similarly, secondary winding is, where is that? Okay, point. Okay, secondary winding. This will. Then leakage inductance is calculated using this formula, and I could get this much of values. Then here is a coupling factor. Now, finally, I am calculating the capacitance of this capacitor connected in parallel, and using, I have to consider the 2% ripple factor. So delta VPP is 0.1 after considering the 2% ripple factor, and my uh, capacitance is 250 microfarad, which is minimum value. Therefore, in practically, you have to consider approximately around 330 microfarad. Okay, then capacitance ESR calculations. You already have a tangent loss given in the question. Now, by using those, your ESR is 0.48 micro ohm. Then ESR voltage jump is approximately something like that, and my capacitive ripple and total ripple is given here. Capacitive ripple is here. Then ripple percentage is 1.56, which is less than 2%. That is beautiful. So here are the MOSFET selection. This is the diode selection and diode parameters. Input capacitor not really required. I haven't used the input capacitor. So finally, I have the parameters here, all the necessary parameters here. And now let's go into the Simulink model. This is my DC source with 170 volt input. This is my MOSFET, PWM generator, duty cycle given here. Okay, capacitor is 330. That is what we got in the calculation theoretically. My resistive load is 1 ohm, and finally let's run this model. By running this model, now you can say that my output voltage is 5.142 and output current is 5.142. So multiplying them together, I could get output of 26. I needed 25 volt. In case of the transformer parameters, this is as per the nominal power 25 watt and switching frequency of 100 kilo ohms, kilohertz, which was given in the question. Then these are the resistance, winding resistance and winding inductance we have calculated, and this is the turn ratio I have used. Generally, in the ideal transformer, you have to use the voltage, primary voltage, and the secondary voltage you are supplying, which is you are 170 and 5. However, you can see that your voltage will be reduced to 9.3 volt, and you are able to provide around 9.346. Okay, so that's why you have to tweak the turn ratio, and you cannot generate 5 volt or 25 watt output. Therefore you have to consider the transformer winding losses, and therefore you have to consider the between the number, what do you call that, you have to do in the turn ratios. My ideal turn ratio was 34:1. Again, this will give me approximately around 3 volt. So considering everything, I'm able to get my required output here. Okay, I have next is the what do you call that, scope. The first top column shows the voltage waveform and current waveform. At the bottom you can see that there is a spike. Initially there is the set, it took some time to settle down. However, this is the steady state of the we have a low ripple, so 5 is always greater than 5, so voltage and current. Okay, this is the waveform. The startup behavior, initially there is an overshoot around 12 volt. This is due to the energy transfer and no control loop. You can see that this model is a open loop, and we do not have any feedback system. So that's why we can see the initial overshoot of 12 volt. However, it rapidly settles to the operating range of 5 volt and 5 watt. Then this is the steady state range. I already have shown you. In case of the current behavior, current follows the voltage because it is purely resistive, and they are in voltage and current are in phase. That's why current follows the voltage. Now what happens if you increase your load to 10 ohm? Then you are getting around 13.26 and 1.23, so your current is reducing, so you are getting approximately 17 watt. And we why your power is reduced? Because your load has consumed some power, right? Therefore it's not 25 watt, it's 17.59. Okay, In conclusion, I could say that we have successfully designed and simulated the flyback converter with the ripple less than 2%, and this is uh, nice, and we can even use this in real life construction of flyback converter. Okay, thank you for your time. Hope you learned something. uh, Thank you. See you in next video.